The experiments we're going to do in this film have to do with vorticity. They illustrate the concept of vorticity in a physical way, and they also show how vorticity can be useful in understanding fluid flows. Let's begin by remembering that the vorticity is a measure of the moment of momentum of a small spherical fluid particle about its own center of mass. Suppose that you had some very complicated motion in a liquid, and that it were possible, by magic, suddenly to freeze a small sphere of that liquid into a solid. During the freezing, the moment of momentum would be conserved. And so it turns out that the angular velocity of the solid sphere, just at the moment of its birth, is exactly half the vorticity of the fluid before freezing. Now, the dynamical theorems of Kelvin and of Helmholtz relate the changes in vorticity of a fluid particle to the moments of the forces acting on that fluid particle. The vorticity omega is defined as the curl of the velocity vector. Each fluid particle has a certain vector vorticity. The whole fluid space may be thought of as being threaded by vortex lines, which are everywhere tangent to the local vorticity vector. These vortex lines represent the local axis of spin of the fluid particle at each point. In two dimensions, the vorticity is the sum of the angular velocities omega A and omega B of any pair of mutually perpendicular fluid lines AA and BB passing through the point in question. In a rigid body, every line has exactly the same angular velocity, so the vorticity of a rigid body is the same at every point. It is exactly twice the angular velocity. This gadget is a vorticity meter, which floats in water with its axis vertical. The two vanes at the bottom are driven by the angular velocities of two mutually perpendicular fluid lines, so the arrow at the top turns at a rate equal to the average of these two. That is, with half the vertical component of vorticity of the lump of water in which the vanes are immersed. This tank has been on the turntable for a long time, and viscosity has forced the water into a rigid body rotation. The vorticity float rotates almost exactly with the speed of the crossed white lines on the bottom of the tank. Sometimes the word rotation is used as a synonym for vorticity, but this does not mean that a flow has to be curved for vorticity to be present. Here, for instance, water flows in a straight channel. The streamlines are essentially straight and parallel to the side wall, but the arrow rotates, showing that vorticity is present. Near the wall is a viscous boundary layer, in which the velocity increases with distance from the wall. Let's look at a fluid cross. One leg moves downstream parallel to the wall, while the other leg rotates because of the non-uniform velocity distribution. So there's a net vorticity, and the vorticity meter spins. On the other hand, the flow may be without rotation, even though it is curved. This is the plan view of a spiral vortex tank. Water passes from the reservoir through a flow straightener and into the tank through a tangential entry. It spirals round and round in a very tight vortex and finally leaves vertically through a drain in the center. What will the vorticity meter do? It doesn't rotate. It moves in pure translation, like the needle in a compass box mounted at the rim of a rotating turntable. Let's look at a fluid cross as it goes round the vortex. Leg A follows the streamline, so it rotates counterclockwise. The angular momentum of the fluid is conserved as it flows toward the drain, so the tangential velocity varies inversely with the radius. This means that the velocity of the inner part of leg B is greater than the velocity of the outer part, and so leg B turns clockwise. The clockwise turning rate of B is just equal and opposite to the counterclockwise turning rate of A, and so the net vorticity is 0, and the vorticity float confirms this. Incidentally, since the two vanes of the float are rigidly connected, the float does not respond to the shear deformation of the two fluid lines, but only to their average angular velocity. There are several theorems which relate the vorticity to the dynamics of fluid flow. One of these is Crocco's theorem, which is nothing but a special form of the dynamical equations of motion. With steady motion, if the flow is incompressible, if there are no viscous forces, and if only conservative body forces are present, then the vector product of the velocity vector with the vorticity vector is equal to the gradient of the stagnation pressure divided by the density, where the stagnation pressure, or as it is sometimes called the Bernoulli number, is the sum of the static pressure and the dynamic pressure and the pressure associated with a body force field. Consider a two-dimensional flow in the plane of the paper. If the flow is two-dimensional, the vorticity vector is normal to the paper, while the velocity vector lies along the streamline. According to Crocco's theorem, the gradient of stagnation pressure is normal to both the velocity vector and the vorticity vector, that is, in this direction, and in the plane of the paper. So the stagnation pressure, P0, is constant along each streamline and varies between streamlines only if vorticity is present. To illustrate, look again at the straight boundary layer. The pressure is uniform across the boundary layer, but the velocity is variable, and so the stagnation pressure is variable. This means that vorticity is present. The velocity gradient is strongest near the wall, and so is the gradient of stagnation pressure. In this run, with a vorticity meter near the wall, the rate of spin is quite large. Here, with the vorticity meter further out on the boundary layer, the rotation is less. And here the float is outside the boundary layer and is not spinning. As it moves downstream, however, it enters the boundary layer, which has grown thicker, and finally begins to turn. When the vorticity is 0, as in the spiral vortex tank, Crocco's theorem says that the stagnation pressure must be everywhere the same. The spiral of the vortex is so tight that it is not much of a liberty to think of the streamlines as being concentric circles. The equilibrium between the net pressure force acting on a fluid particle and the centrifugal force requires that the velocity v vary inversely with the radius r if the total pressure is to be constant throughout. This velocity law is exactly the condition required for the free surface to be a hyperboloid. Now the flow is being decreased, and you can see that the hole in the core doesn't really extend downward indefinitely. The infinite velocities and shear rates theoretically at the axis are undone by large viscous forces which come into play there. But as we increase the speed again, the vortex strengthens, and the bottom of the hole drops out of sight. An irrotational flow may contain singular points, where the vorticity is infinite. In the spiral vortex flow, a highly concentrated vorticity exists right at the center. Look at a fluid cross right at the center. Only at this point do both these arms rotate in the same direction. Now we come to a new idea, the circulation. Remember that the circulation gamma around any closed curve C is defined as the line integral of the velocity v around the curve. Now the circulation theorem relates the circulation around any closed curve C to the vorticity passing through any area bounded by C. Specifically, the circulation gamma around C is equal to the flux of the vorticity vector omega through the area bounded by C. So if there is a definite circulation around some curve, then the enclosed fluid must have vorticity. But if the circulation is zero for every curve in a certain region, then the fluid in that region must be entirely free of vorticity. Sometimes the vorticity is everywhere in the fluid, distributed throughout. But often the vorticity is very large in a thin thread of fluid, while the remaining fluid is without vorticity. Then we can simplify our thinking by lumping all the vorticity into a concentrated vortex core around which the fluid spins, and then by pretending that the remaining fluid is entirely free of vorticity. The vorticity is infinite in the core, because a finite amount of vorticity has been dumped into zero cross-sectional area. Now let's look at the circulation for a small circuit in the straight boundary layer. Because of the distribution of speed, there is a net circulation, which is in fact related to the vorticity of the enclosed fluid. In cross-section, a single vortex line with non-vortical fluid outside appears as a point around which the fluid moves in concentric circles. The velocity varies inversely with radius. In the solid body rotation tank, the vertical vorticity is everywhere equal to twice the angular velocity of the tank. Every horizontal circuit you draw has a circulation equal to the flux of vertical vorticity through the area bounded by the circuit. In the spiral vortex tank, the flow is non-vortical, except for the concentrated vortex core, which accounts, so to speak, for the whole motion. All fluid circuits surrounding the core have the same circulation, because they contain the entire vorticity flux. All fluid circuits not surrounding the core have zero circulation, because they contain no vorticity flux. A wing generates lift because of the higher pressure below and the lower pressure above. According to Bernoulli's theorem, the velocity on the upper surface must be greater than the velocity on the lower surface. This means that there is a net circulation around a lifting wing. Often we pretend that this circulation is produced by a vortex, which is bound in the wing, and which accounts for the circulatory movement. We don't care whether the vortex is really there. We care only about the circulatory velocity field that it creates. The circulation is important because of a powerful theorem which Lord Kelvin evolved from the dynamical laws of motion. This states that the time rate of change of circulation for a fluid line of fixed identity is governed by the torques produced by all the forces acting in the fluid. The torques due to the pressure forces, to the body forces, and to the viscous forces. Let's look first at the torques due to the viscous forces acting on a fluid particle of fixed identity. You can see from the force diagram for this fluid particle that the viscous forces can produce torques about the center of gravity, the center of mass. These torques are capable of changing the vorticity of the fluid particle, and thus the circulation. Here in the straight channel, the vorticity float moves downstream without turning because it is outside the boundary layer. But as the viscous layer diffuses outward from the wall, the fluid in which the float travels finally reaches a position where viscous forces create a circulation, and with it, vorticity. Here again is the tank on the turntable, with no motion and with no circulation. Now the turntable has started, but the fluid in the middle doesn't move because none of the agencies which create circulation have yet come into play there. Next to the wall, however, the fluid does circulate because of viscous stresses. These viscous forces gradually diffuse outwards from the wall, and more of the fluid circulates. In the end, viscosity brings all the fluid into a perfect solid body rotation. At this point, paradoxically, the viscous forces have vanished altogether, and there is nothing to force further changes in circulation. Now the turntable has stopped, but the motion continues unchanged, except near the walls of the tank where viscous forces act. The retarding viscous torque diffuses inward and decreases the circulation more and more until finally the whole fluid is at rest. When a fluid flows around a sharp edge, viscous forces in the boundary layer produce a separated flow. The fluid which has been affected by concentrated viscous forces forms a concentrated vortex. We can make the strength of a vortex visible by a ping-pong ball which remains in the dimple. The rate of spin, though, decreases because of viscosity, which spreads the vorticity of the core into the surrounding fluid. Now let's look at the body forces G as a circulation changing factor. If these are irrotational, that is conservative, this term is zero. But for rotational body forces, that is non-conservative forces, this term is generally not zero. Look at this small circular piece of fluid. If the net body force G passes directly through the center of gravity, this force produces no torques to change the circulation or the vorticity. Centrally directed forces like gravity are of this type. They are irrotational. There are two important rotational forces which change circulation and vorticity: Coriolis forces in a rotating reference frame and electromagnetic forces due to the flow of an electric current at an angle to a magnetic field. In both these cases, the line of action of the body force need not go through the center of gravity of a particle. Because of such forces, the oceans and the atmosphere are full of vorticity, and so are magnetohydrodynamic flows. Does the vortex in the bathtub always turn in the same direction? Does it depend on which hemisphere you're in? You can't really tell in the bathtub. The Coriolis forces due to the Earth's rotation are incredibly small, only about 1/1000th the force of gravity. But we've built an apparatus in which this is the dominant force. This large circular tank has a very small drain hole in the center. The tank is being filled with water, swirling clockwise. Remember, clockwise. We waited a day to let the motion die down. Now the clock has started, which means that the plug was pulled from the drain hose. This is a small vorticity float with its vanes entirely submerged. For several minutes, nothing much happens. Let's imagine that this is the drain. The water flows readily inward from all directions. The Coriolis force acting on a fluid particle in the northern hemisphere, as it moves radially inward, is circumferential and counterclockwise. This force, integrated around a circle, contributes a counterclockwise torque in Kelvin's theorem. This tends to make the circulation increase with time counterclockwise. In the reference frame of the Earth, a fluid circle, which starts at one radius with zero circulation, acquires, or should acquire, counterclockwise circulation as time proceeds. Now, back at the tank again. At 9 minutes, there is still no perceptible motion. But at 16 minutes, we begin to see a distinct counterclockwise motion. At 24 minutes, the slow turning of the Earth has been enormously amplified. Although the Earth's Coriolis forces are very small, they are extremely important to our everyday weather. They can also generate hurricanes. If the conditions of temperature and humidity are such that there is a strong local updraft of air in some region, air must rush in from the sides and up the updraft. This is nothing but the water tank experiment upside down, and a strong vortex is formed.